have shown you part of our work on polypropylene reinforced fly ash. And this will show some extra features. Remember in the earlier lectures where we put polypropylene fly ash, we did not mention anything about modifying the surface of the fly ash. Because if you put fly ash in polypropylene, sometimes you can get drop in strength and other things. So that kind of thing can happen in many parts. So for example, if you put glass fiber in resin, often you put a surface coating agent. What is that called? Can you speak up? The question is, you put a coating on the glass fiber. Before you put them in the epoxy. Coupling agent. Okay, and yeah, the same thing. So in our previous lecture on the fly ash polypropylene, we did not mention the effect of the coupling agent. Okay? So I thought we have done that, and you see the strength of the poly, some of it goes down. But I thought in the final lecture, I'll show that actually even like composites, fiber composites, you can also put a coupling agent on this fly ash, because fly ash is also kind of, it's ceramic. They are not all glassy. Only one or two components are glassy, but they are all crystalline part. But they are still ceramic. The advantage of a coupling agent is that it makes the matrix and the fiber friendly and attractive. And stress transfer and strength transfer can happen without any concentration. So some of the slides in this one have been shown, but now we also include the slides using the coupling agents. All right? After this, the next will be a tutorial. There's a tutorial 5, which will show some more features. Now, as you have seen, polymers have a lot of calcium carbonate. And calcium carbonate is quite light, but it's also quite expensive. And the advantage of fly ash compared to calcium carbonate is that fly ash is even cheaper, lighter, and wider particle size distribution. Wider particle size and distribution. Disadvantage, more inconsistent due to chemical composition, more contaminant, especially unbound carbon, and more abrasive. So that way, if you put the fly ash and under tension, even the fly ash can cause stress concentration in the polymer. So particularly in polypropylene is a kind of not very ductile, it's kind of brittle. So if fly ash cause abrasion there, that could be a reason why the tensile strength goes down. Okay? So these are the things. Whenever you see something is happening, it's worth looking into a solution. So whereas fly ash had advantages, they also have some disadvantages. But everything has advantages, everything has disadvantages. Can you say a single thing which does not have any disadvantage? Maybe if you get money, a lot of money after that, after the day, all right? But if you have a lot of money, if you are running with money, if you lose the money, then it causes a lot of disadvantage. So money is good, but if you lose the money, then it can cause disadvantage. So everything has advantages, everything has disadvantages. And people think everyone has disadvantages excepting they themselves, all right? But some other, that's a good way of thinking. All right? Some people think they are the greatest, they have no disadvantages, and some people think, oh, we are so disadvantages. The best thing is make a combination and a compromise. And that's what fly ash tells us. It says, don't worry about it. Now, this is what we have done before. Whiter product than normally fly ash filled polymer. This is, you have seen some of these things. And to compare Australian fly ashes regarding as filler in polypropylene composites. And then to get polypropylene composites with mechanical properties at least as good as pure polypropylene. So remember, we have seen that in polypropylene fly ash, the tensile properties go down. So here, this work of Dr. Akmas Deni, it wanted to see, can we put some coating onto the fly ash, and then that can actually be a coupling agent and will prevent formation of defect during the tensile strength. Okay. Polypropylene, it was powder. MA5, what is MA5? Male flow index 60. Does it mean is it more liquid than male flow index of 6? Which one is more flowable, male flow index 60 or male flow index 6? 60, thank you. Because a lot more mass flows under a certain force, because it will not flow so easily because polyethylenes they are viscous liquid, but if you apply a stress under the constant stress over a period of time, for example in 10 minutes, it will flow maybe 60 grams. So that is what the male flow index is. It's very straightforward. And it was obtained from this company, and their product code is, okay, Martog and Company, and their product code is 617OH. And the fly ash, there are so many types of fly ash, particularly supplied by this company, Cementos Lab Brisbane. Now, because this is the final lecture in this series, so some of the things which we have gone through, it is what putting some of the things there, because then it remains in your mind or memory, all right? Chemical composition, TGA, thermal gravimetric analysis, particle size and distribution. Okay. Surface morphology as obtained by SEM, appearance and density. These are the characterization of the fly ash particles. And this is something which we have seen earlier, but it is worthwhile mentioning. All these 4 fly ashes, they have similar silica and also pretty low calcium oxide, so all of them are F-type fly ash. And then if you go to the LOI, the first one has the lowest LOI, and this is the middle, and the other 2 have quite similar LOI. So that is how the composition looks like. So all 4 of them are type F fly ash because calcium oxide is very low. Now the chemical composition, if we have, when we do it ourselves, QM scan, this is an equipment, okay, which actually available in the labs, and that way, the mineral composition, like silica group, aluminum silicate plus potassium, all these things are given there, and the maximum thing is the aluminum silicate, combination of aluminum silicate is about 70, and silica group about 24. That's about 94%. The balance of them, about 5.5. Out of that, titanium silicate is about 3.62. So which means you have silica, but silica is can be also in different forms. So that's what it shows. That it shows that the mineral composition of the T63 fly ash can be like this. This is not the formula of the thing, but combined mineral composition. If you have silica, you have so many silicates and things like that, aluminum, okay. This is the funny thing. So this is nothing, this is nothing attractive, but sometimes when you go to the website and you click something, a nice picture like that comes up. And I thought that's a good thing to look at. And when you look at that, on the right-hand side, it gives all this titanium silicate, corundum, Fe oxide, and all those things. So it puts something like that. And also it puts particle size like this. So it must be some kind of email which send a message to me saying that, yes, you and I are working together. I thought, thanks for coming back. Okay. So if something like that comes up, it gives a break, like a tea break. Okay. So I just thought, because it came there, I didn't want to throw it away. What is? Oh, these actually, I think, highlight some of these oxides or things like that. You have some color here, some color there. It might show more concentration or something like that. But it doesn't tell me. So it's like it has sent a problem to me and say, solve it and get it back to me. So if you get problems like that, but that was a good question. So I also used to think what that white yellow thing is. So there are two of these yellow compounds. Okay? No, it's not optical microscopy. This is an email message. There's no optical microscopy. These are sometimes emails. They try to work out how they can identify by color. So they put colors and things. It's not optical microscopy. But this is you're asking, what is this? They take data from all published literature and they try to put it color. All right? You can do something similar. And sometimes it can also be different companies. I get a Marquis. Have you heard from Marquis? Do you get an email from Marquis? MRQUIS? Okay, if you don't get it. Yes, something like, yes, you are right. Yes. But that's something which we did not generate. But I don't know. My student may have generated me, but I'm trying to contact him, but I'm not getting any answer from him. And now he's working in different fields and things like that. But Ahmad Zaini, all right? I looked at it. I was trying to confirm it. Ahmad, what do these things? But he does not. But this is what I understand. So he also was funny. So he came from Indonesia and he has a very different brain. And he also used to, so he might have developed something like that and he put it in there. Dr. Bando, this is for you. Try to work it out. I said, I cannot work it out. But thank you, Dr. Das. You have a good brain. And now I'll go back to my student. I'll say, now this is what it is. All right? Oh, did you come here? All right. Yes. Now I can see there are, before going to that, there are even some greens also. And here you can see two greens also there. So there is color matching. So maybe it might show that you have 1,000 or 200 points, and some of them are more and some of them are less like that. The aluminum silicate is the largest amount here, blue, and you see too much of blue points there. And in one of the tables which were gone earlier, I think aluminum silicate showed about 70%. So it could be something like the same thing. It might indicate the particle size and things like that. All right? And as soon as I mentioned that, in bottom, it also mentioned this is the scale bar. If it's this is 10 micron, if this is 20 micron. And if you go to something like that, this is about 425 microns. So this could be scale bar on the basis of that scale. Okay. Thanks for explaining that, okay? At least I'm happy that I'm getting, because I didn't understand, what do all these things say? Okay? There are so many ways of analyzing. So this could be the particle size distribution. So if this is a composite, and you have the polypropylene, and this is how the particles can break in size and their colors. And so composites are not easy. But if you don't look at that, and if you make the composites work, it's like when you eat a sweet. You eat it, you enjoy it. But if you go to a food scientist, the food scientist will do all their analysis and pass it on to you, including all vitamins, this and that, and things like that. And the last thing I ever like to do is to eat and go to a doctor. We'll say, do your sugar checking. I never do all those things. All right? Because then everything will, you say, it gives you the breakdown information. So to different scientists or different professions, those things are attractive. Okay? Okay, thanks for clarifying that. And because you are a chemist, you have a good brain, a different brain than me. So now I can see your view. So these are actually particle size distribution and things like that. All right. So big hand for you. Thank you. Okay, now if you look at particle size distribution method and light scattering, so particle diameter, so before light scattering and all these things, you actually see these kinds of graph. So this shows particle diameter, maximum diameter is about 100 here. And they're in this size. Volume percent, if you go for volume percent, and if you do this, so this is another method of light scattering. Now the overall particle size and distribution, mean, mode, and median. Mean, mode, and median comes from all these things. If you take means, if you count all the particles, their size divided by the number, then you get mean. Mode is another aspect, and median is. So from the same graph or same picture, you can come up with 3 different values to summarize them. So this comes like this, about 86, 106, and 67. So mean is in between them. Mean is between mode and median. And this shows that this particle is much higher in size, T57, but the other 3 is less than 40 micron. So that is, they are quite useful for using in fly ash composites. Now, when he said mean and after, what he had done, he had given a surface coating to this fly ash. Now, it's a confidential surface coating, but I have a feeling it's something similar to what you give to this coupling agent. Okay, so he had used a coupling agent, and before the coating, the fly ash particles are separated, but once you have the coating, then the fly ash particles get attracted to each other, because here if you do not have the coating, then they are not attracted, but once you have a coating, then they are attracted. Can you see that? The fly ash particles in the matrix and things like that, they are attracted. So the matrix does not see any new thing, unfriendly thing. So this is the part which Dr. Ahmad in his work is very attractive to me. Because when we say about if you have a coupling agent, there is coupling now. It shows here now, the particles after putting the coupling agents. These are the before, and this is how they are after. So this is how, for all these 4 fly ash things, he has shown. Now the modification of the fly ash color, you have seen this beforehand, near gray black to white bending. And people can do that. For example, Dr. Bhabatosh, he said that he has put the fly ash in some high temperature and the fly ash changed color to quite whitish. So this is quite commonly observed thing, okay? And now this is another fly ash, another gray black fly ash, and if you give near whiting thing, it comes up like that. So different fly ashes show different things. This is a third fly ash, also it shows a bit more whitening. So these types of things can happen in different grades of fly ash. So all of them may not go to pure white, but they may become much lighter color. Now the standard illuminant, daylight after blue sky. The color measurement is done by standard illuminant, and that is the daylight under blue sky. The CIE 10 degree standard observer, geometry of 0, which is normal incidence, and barium sulfate as standard white. So these things give you the coatings like that. So before, so if you have T59, one of the things, this is the one, and T59 after the coating, you actually give the wavelength and intensity. So you can see that before and after the coating, all of them are modified. So then T64 before, T64 after, what is this angle? And then when you give the coating, it reflects much more of the light. That means it actually tends to become more white, reflecting. So this is how the earlier, when we had presented some of the earlier slides for Ahmad Zaini, we did not have the modified by this coupling agent. We did not have those graphs. Okay, so now here we have the before giving coupling agent and after using coupling agent. So that is what is worthwhile. Calcium carbonate is given on the top. This is not used in this material, but calcium carbonate is a standard material, standard white. Next to barium sulfate, calcium carbonate is considered as very high. So if you want to, what it shows that if you want to have the whiteness of calcium carbonate, you have to reach that level. But, so which material shows you closest to the calcium carbonate? Can you look at it and say from there? Which of the graphs is closest to the calcium carbonate? Can some of you come here and show me using this? Second person, yes? Yes? On the graphs, which graph is closest to the whiteness of calcium carbonate? Which graph which one is the calcium carbonate? On the top. And which one is? Just the one just below that. So what is that one? T64 after. So which means that if you do this color analysis and then it tells you numerically and scientifically which one, after you have put the things, which gives you the best color, or if you have removed the things. So that is a very indicative way of doing that. And which one has the lowest whiteness? So these two. All right? Okay, yeah. So this is what, as I have said, using equipment in the optometry, division of optometry. So there are doctors and things like that, and they look at your eyes and things like that, but these are the kinds of equipment they use. And I was so happy. One of my students, Chinese students, he came and he he was for masters, and then just before he went back to China, he sent me an email and saying that, Dr. Bandu, please have a look at this. And I found that it was a couple of minutes video he has put on me. And one area he says, Dr. Bandu never sleeps. And I said, how did you know that I don't sleep? And because when I have all these things, it's true actually. I never sleep. I don't sleep even for 2 to 3 hours at night. But how did the student come to know about it, Chinese student? I don't have that video right now, but I can send it to you. But he actually kept on singing, Dr. Bandu never sleeps. And I said, hang on, I don't want to show this video to my wife. Then she said, you go to bed and you still keep on thinking and all these things. But I cannot help that. Because now that I think when I'll be walking, all these things will be coming to my brain. And that's what I think you guys and girls are also like that. And that's what is about science. All right? Science and engineering. But this is fantastic. So that top level is calcium carbonate. So it's about normalized intensity. It's about 0.92. And barium sulfate is still higher, but it did not have the barium sulfate. Calcium carbonate is easily available, but barium sulfate can be still a bit higher. So does not matter how you, yes?
So in the earlier slide you have mentioned that barium sulfate is the standard and for whiteness. Here you are doing carbonate.
Okay, because calcium carbonate is normally used in all polymers as fillers. And that is the whitening agent also, calcium carbonate. Barium sulfate, it is, as a composition it is like that, but barium sulfate is not used there. So that's barium sulfate in the instrument, or barium sulfate is a Nobel Prize winner. So it sits on the top, but calcium carbonate is not a Nobel Prize winner. It's a simple person like me. Okay? So I'm no one near the Nobel Prize winner, but I love my students, I love my colleagues, I love things. Interact with everyone. That's calcium carbonate. And calcium carbonate, but it's a mineral. If you can save it, you can use it for other purposes also. So using calcium carbonate as a filler is very attractive because it gives you all this whiteness and the things like that, okay? All right. I remember Dr. C.N. Rao once said, he said his Nobel Prize nomination went a couple of days later, so that's why he was not in the consideration. So I feel very sorry for him. He's a great man, okay? But for whatever reasons, I'm quite happy. All right? I mean, I'm happy for me, not happy because he was unhappy. No. At IIT Kanpur, when I did my MTech, that's when he used to teach chemistry. And what a great guy he was. He used to walk like that and his name is C.N. Ramarao, but he used to call him C.N. One day I had asked him, what does R stand for? Is it Ramarao? He said, why do you not use the word Ramarao? But anyway, he's a great man, and then he moved and things like that. So I'm very happy that I was a student and I learned a lot from him. And he brought the chemistry in such a simplified way, all right? But as I said, I'm an ordinary man, nowhere close to Nobel laureates, but I enjoy these things. So now that the Dr. Das, he explained, and now he explained that diagram, whenever I will walk through the road, all those diagrams will float in my mind. Okay? And I want the same things to happen to most of you, at least whatever of the slides, whichever of the slides you enjoy, okay? Please enjoy it, all right? Does it answer your question? So calcium carbonate has very high whiteness, and barium sulfate has still higher whiteness, but because calcium carbonate is such a popular material, mineral, so most of the time it is considered as the highest whiteness. But then when you, other people, someone said no, barium sulfate, because when you do that. So when earlier we used to compare with calcium carbonate, and we have compared with barium sulfate, and we found that this is almost 95% of the barium sulfate also. The L, A, and L star, A star, and B star value of fly ashes. Okay. Now, what L star means here? It represents lightness ranging from 0, which is black, to 100, is white. So calcium carbonate is 96.9, and because people use calcium carbonate and so have not gone for barium sulfate, it will be not much different. It will be slightly higher than calcium carbonate plus. Now, calcium carbonate is 96.9%, and it's reddish when positive and greenish when negative. So it is negative, that means it's a bit greenish. Yellowish when positive and bluish when negative, so this is a bit yellowish. That's what some of the fly samples which you have seen that. And T59 before this surface coating is 69.8. 0.24, and after surface coating, it goes up to 76.1, 1.4, and 9.4. So it goes up significantly. And likewise, this is before and after. So the after properties, after those coatings, it goes up. And all the things, after properties, they go up, except for this material where the A star goes down. So this is another way. Again, this is quite a new way. Today being the 15th lecture, okay, I thought it will be worthwhile for you to see, have this information. And again, if you want these slides, first approach Professor Kaur, because this GIAN program is through him and signed and all these things. So please request him to provide you something. But otherwise, if you need any particular slides, as long as they not the entire file, I'll be happy to pass on to you. Okay? But here we see a new way of identifying the color content and how the color properties of the, not only for fly ash, you can look at for many other types of things. Okay? So if you know someone who works in the optometry section, please invite him or her to be part of your team. So, and they will also like it. All right? And please make sure that you include them as a co-author, because that's what I did when this work was published in Fuel. I asked Ahmad Zaini to include the name of that professor from optometry. This table is also very useful. So here represent lightness ranging from 0, black, to white. So all of them are, all these for fly ash is at least 75% white, and it goes between 70 to 69.8, about 70 to 75% white. So their deviation from calcium carbonate is about 30% of that value. All right. So this is density and average particle size of fly ash density. So it goes up like that. Loose density, tap density, after, before. These are different ways by which this density is. Loose is if you have loose particle, and tap means you actually put them in a cylinder and things like that. Tap it means make them a bit dense, after for some time, and then look at it. All right. So loose density is the bottom one, and tap density is the higher one. So there is significant increase in tap density. All right. So that is something. And if you can keep on tapping more, after some time it will become perhaps a bit constant. And if you have average particle size, that also affects it. All right. You get higher density with average particle size, and also after tapping. Have you ever done any tapping? No, this is, if you're working with particles, it's worth doing some tapping things. There are standards, okay? Tapping, and then thereby introduce those tapped blocks and things like that as block reinforcement. There are so many ways to improve things. Mechanical testing, tensile and impact testing. This is the Young's modulus of the as-resist fly ash and then filled with polypropylene composites. So all of them go up. Some of them goes up by the most. There are 4 different colors. But in general, so the modulus goes up from about 17500 to the highest about 5500. That means about goes up by another 200%. So it becomes whatever value is here without fly ash, you get about 3 times the modulus there. Tensile strength of as-resist fly ash, as we have seen earlier also, it comes down, but here it comes down from about 30 to about 15. So this is actually without the, let's see when we give some coating. Okay, we'll see the coating slightly later. And this is the fly ash reinforced polymer, plastics, T63, that fly ash, and it shows these different kinds of, this is 4 micron, 3 micron, 2 micron, 3 micron, 3 micron. So not much difference. Effect of treatment on Young's modulus. So if you are giving a surface treatment, the Young's modulus again goes up before and after. This is before, this is after. That means with treatment, the Young's modulus, particularly for 40% fly ash, it goes up, or with 20% fly ash, it goes up by most. If you are putting the coupling agent, the Young's modulus goes up considerably. And this is for T63, this pink one before, and this one is T63 after. So this goes up by slightly, but T64 increases significantly more. Effect of treatment on tensile strength. Now, if you remember, in the earlier figure, the tensile strength, lowest value of the tensile strength was about 15 MPa. In this case, it still goes down, but this tensile strength value is about 20 MPa. So it goes up by about 5 MPa. So if you are giving the coating, this, okay, so it goes up by some amount. Comparison before and after treatment. So this is before and after. There doesn't look much of a difference, but this one is T64 before and T64 after. This shows a more voids and things in the fly ash. These are actually large failure, and there seems to be some more surface area. This is more flat compared to that. So you get some improvement in the strength. Notched impact, original fly ash and polypropylene composites. So you have highest about, okay, without with fly ash 0, it's about 1.75, and there it goes up to, some goes to 2.5, some goes to about 3. So that is still an improvement. That's a good thing about impact property. And again, effect of treatment on notched impact. Again, it's still similar. So it does not go down. See, the highest is about still 3 compared to about 1.7. So all of them have an increase in the, so at least the fact is that if you are giving a surface coating or coupling agent, it's not reducing the impact strength, because impact does not give any time. So at least people will ask the question that if you has, without impact, if it has improvement in impact strength, if you give this surface coating, will the impact strength go down? So you have to also prove that no, the impact strength remains the high thing. The good things, if it remains at that level, that is good, and the bad thing, if it improves, that is also good and better. This is the thermal behavior or endothermic segment of polypropylene. We have not so far shown any of these in the earlier ones, but most of you are familiar with, or at least the material scientists and the chemicals. So what happens, this shows that when you are heating the polypropylene, it comes on, and this is the melting point. Remember, in one of the things we had said that polypropylene has a melting point, and this is when it goes up. Sometimes if you are not heating, but if you are doing as a function of frequency, sometimes below temperature, similar graphs you can see for inverse or things like gas transition temperature, but please don't get confused. This is the melting point, okay? Temperature, endothermic heating. What is endothermic heating? Is you have to keep on put heat into it, and that then becomes more and more, and then when it reaches this heat flow starts coming down. So this is the melting point, and they take this slope like that, and this is the area when it actually, you started having, this is about 150 degrees C. That means it starts becoming very soft, it starts flowable, and it becomes the melting point. So this is the thermal behavior. And exothermic cooling, so now if you have a molten things, if you start cooling, then you get temperatures. So the cooling segment of polypropylene comes around this. It starts solidifying anywhere below that. So this is when you're making the components, you have to take into account both these things. And the crystallinity of T63 filled polypropylene composites, the crystallinity after treatment is higher than that before treatment. So even if it goes up from like 48 to 53, 54, at least it is somewhat higher. And even if you go to up to 50 weight% fly ash, or this is 40 weight% fly ash, it is still higher by 5 to 7%. So crystallinity is a bit better. If you now get 5% or 10% better, that is better. All right? It makes the material, that is what makes the material a bit stronger after treatment. Correlation between crystallinity impact and tensile strength. This is before treatment. Oh, that friend has come back on the screen. So that fly, it likes all this polypropylene and all this information. I mean, it is flying, it will go back to its class and you will teach all these things. So this is, you have seen that the tensile strength goes down from 30 to 20, and then impact goes up, impact on this side, and crystallinity goes up to about 20%, and then starts coming down. So this is how it happens, and let's see, oxidation, induction. This is something what happens, the heat flow and oxidation may start happening, and this shows that after treatment, you have a higher oxidation inflow temperature, and before treatment, you have this lower one. So this makes it oxidation property much better if you are giving a treatment of this coating. It's not, LOI is related to the carbon, but oxidation, I don't know. But it could be related to that, but I really don't know. That is, now they are looking at the properties of the entire material, oxidation, induction time. So it shows that the way I look at it, it shows that it can withstand more oxidation. Maybe because you are having the coating is giving some copper on the polypropylene also. So it's also preventing its oxidation as a function of time. So that is what oxidation induction time. So it takes more time for any oxidation to start. And I think it's because of the coating. All right? But that was a good question. Conclusions and suggestions. The whiteness of fly ash can be increased up to 93% without changing the inherent properties. And that's what you have seen. One of the fly ash goes very close to that top line. Fly ash can be used as filler until 80 pHr. Composites contain treated fly ash have better properties compared to the untreated ones. So that's what he said, that you can use fly ash, but if you can, before putting fly ash in the plastics, if you can give it a treatment, then it will provide better properties. So that's where it shows that polypropylene, although some of the properties can go down, but you can also actually improve the properties of the composites, because polypropylene has a higher modulus. Polypropylene has better attraction also. It can be used in like water pipe and anywhere it can be used. And if you can improve the fracture properties, then it will be quite safe. Okay? So this is the end of the 15th lectures. So we have one more hour after time when we'll have tea break and things like that. But in the meantime, if you have any question, you can ask me.